Hey guys, welcome back. I've got a really fun one for you today. So we finished up our test from the first unit. You can see how you did. These are our three classes, first, third, fourth, and seventh. You can see by standard how it broke down with mastery. Mastery is like achieving 75% of those problems that you got right or more on average. On the bottom here, you can also see the average test scores per class. So it looks like first hour had the highest average test score. Seventh hour had the second, and then third and fourth hour were tied after that. So overall, you guys did really well. Most of you guys are doing great. I noticed a lot of people who are turning in a lot of their homework tended to do really well. Those that got behind on the homework or didn't finish all of your homework or didn't do all of your homework tended to not do so hot. So whatever happened, just do a quick reflection and think how you did. Did you do as well as you wanted to? What can you do differently this second unit? Now that we're all starting off, no one's behind on homework anymore because I'm not taking any of that late homework anymore. So the good news is we're all starting with a clean, fresh slate, so that you can start over and whatever adjustments you need to make so that you can be more productive and make sure you're staying caught up on your assignments. Maybe joining the live office hours if you need to have your questions answered that day probably would be a good idea. This next unit's going to be pretty short, not as long as the last one, so we'll be through with logic and reasoning pretty quickly. I think you guys are going to enjoy it, and today's lesson is a lot of fun. We're just going to talk about patterns. All of math is kind of based on patterns, so if you like math, you probably like patterns, and hopefully you'll find what we get into today interesting. Got a lot of media for you. Anyway, so overall, you guys did really well. If you're worried about retakes, typically when we're in class, we would be able to do retakes, but since we're doing distance learning, it's not going to work that way. If you didn't do as well as you wanted to, good news is when we come back after fall break, hopefully we come back. I think we will, but when we come back, I'm just going to be positive. When we come back after fall break, then we will take a midterm, and that midterm test over the first three units that we get going over during our first quarter, that test can replace your test scores if you didn't do very well. So if you had a rough first unit, but you turn it around and you do better on the second and third unit, and you do well in that midterm, we can replace your test score from the first unit with your midterm score. So that'll be kind of what you have to look forward to when it comes to like retakes or something like that. So let's get started without any further ado, because I got some cool stuff for you. So first, a bit of history. So logic, actually, the fathers of logic would be George Boole and Augustus de Morgan. You can see the years that they were alive in. So George Boole, actually did a paper on him when I was in college. A really interesting fellow. He was the son of a shoemaker. His dad was a shoemaker. He only attended primary school, so through, I believe, like a fifth grade education. After that, his parents had to stop paying for school because they didn't have a free and appropriate public education like we do in America. So they had to pay for all the school, and his parents couldn't afford it, so he only had through fifth grade education. At the age of 16, he started tutoring, I believe, and he became the primary breadwinner. So at the age of 16, he was making more money than his dad was, so he was supporting his family. At the age of 19, he founded his own boarding school, which is a school where the children or the students, they stay at the school. So it's a boarding school, so a private boarding school in England, I believe. And then while he was teaching at this boarding school, he taught himself calculus by reading a textbook, which is pretty impressive. That's how he continued his education. He just taught himself. By the age of 34, he started. I believe that's when let me think, I'm trying to remember. That's when he started teaching at a university. He also started publishing some books, and he started getting into logic and published books at a university in Cork in Ireland. And at the age of 49, that's when he died. So the story is he was a very devoted teacher, and he was walking to school one day, and it was pouring down rain, and he was running late, and he came to the school even though it was raining, and he got soaked to the bone, and he later developed pneumonia, and I think died 3 days later or something like that. So poor guy, died for the cause or whatever. But anyway, another thing is De Morgan, Augustus De Morgan, was a contemporary of his. He also came up with De Morgan's laws, which if you studied logic would be something that you would have heard of. So what I'm trying to say is that logic and statistics, another subject that I teach, are actually relatively new, and so they only go back about 200 years that we've been studying logic and statistics. Now, logic actually led to digital electronics, which is incredibly important with all the ones and the zeros, and I'll show you an example of that in the next page. And if we didn't study logic, we wouldn't have computers today. So logic as the foundation of electronics. So a chime to remind, this is a simple example of electronics kind of program that you can write or something. So the idea is that if the key is in the ignition, or the lights are left on and the door is open, then an alarm or a chime will go off. So if you try to exit the vehicle when the keys are still in the ignition and your lights are either left on or your keys are still in the ignition, a chime will go off to remind you so your battery doesn't die, or you don't leave the keys in the ignition and somebody steals your car. So the way that we would accomplish this simple program is using OR and AND gates. So the first one is an OR. So if your keys are left in the ignition or the lights are on, then it'll go on to the next one, and the second gate will have an input for the AND from the keys and also, or the lights, and from the door. So let's say ones are on and zeros are off, right? So let's say that your key was left in the ignition, the lights are not on, and the door is not open. So the door is closed. So in the OR gate, we have to have one or the other or both, and we do have an input of 1 coming in from the key. So we have an output of 1, and the output of 1 goes to this side of the AND, but the AND, unlike the OR, requires both of them to be on. So since we had a 0 from the door, the output of the AND would be 0 and the chime would not be sound. But if we redid this and we changed it, let me change colors, and now we open the door, so we have a 1 coming from the door. Okay, so now that we have a 1 from the key or the lights and a 1 from the AND, now the chime would go off. And the same thing would happen if we change this, if we put the lights on. Okay, so one or the other or both, so it's still a 1. Or if we change this one to no key, it still would have an output of 1 and still the alarm would go off. So all possible combinations of keys, lights, and doors, this will be able to sort out all of those combinations and know exactly when to turn on the chime and when to turn off the chime. So anyway, really simple digital electronics. If you enjoy that, you should take an electronics course that we offer them at Putnam City. Or if you want to do engineering, like I did, Pre-Engineering Academy at Francis Tuttle, I was able to take a digital electronics course. I think it's a lot of fun, really cool stuff. Anyway, so more repeating patterns. This is kind of stuff just feel like kindergarten. So I taught you guys the times table area thing from 4th grade or whatever. And now we're talking about patterns. So we have red square, blue circle, red square, blue circle. What comes next? Red square. Okay. Then we have yellow circle, green diamond. It's definitely a rhombus, but diamond is what we would have called it back then. Green diamond, yellow circle, green diamond, yellow circle, green diamond. Right. All right. So basically these are simple repeating patterns with shapes. What we end up with is a string of elements that are repeated. So on the first one, our string of elements that are repeated is 2. So these 2 are repeated over and over and over again. So after 2, it just starts back over. On this one, we have a string of elements of 3, and after each 3, it's repeating over and over again. So whenever I was in school, I used to get in trouble, I think, like kindergarten, 1st grade, whenever they taught this kind of stuff, because the teacher would give us a sequence, like let's say triangle, circle, triangle, and there was nothing else that was shown, just triangle, circle, triangle. And the teacher would ask, is that a pattern? And I would say, yes. And the teacher would get really frustrated at me because that's not a pattern yet. But and I would say, well, yeah, sure, that's a pattern. Triangle, circle, square, circle, square. It can be made a pattern by repeating it back, right? Square, circle, square, square, circle, square. And you could just loop those 3. So no matter what string she gave me, I could always make it into a pattern by just repeating back whatever she said. So the teacher got really frustrated with me because what she meant to say is, has a pattern been established? So if we had a square, circle, square, that has not established a pattern yet, but square, circle, circle, now we've established a pattern, square, circle, circle. Okay, so anyway, I would get in trouble because the teacher didn't know how to precisely explain it, or maybe I didn't listen. That's probably more likely it. All right, so we have different ways that we can do different patterns. One of them is an arithmetic sequence, which is when we're adding. So we're just going to add a common value each time. So we have 1 to 5, so we're adding 4, so plus 4. And then 5 to 9, which is still plus 4. And then, yeah, then the next one, we're still adding plus 4. So each time we're just adding 4 more. So what would come next? It would be 17, right? I have to click again. And then after 17 would be 21, and then we'd have 25. And we're just adding 4 each time. That's our common value. All right, on the next one, it's subtracting, but it's still fine. So it looks like we're subtracting 3, subtracting 3, subtracting 3. So next we would get negative 10, negative 13, negative 16. Anyway, so really simple, just arithmetic sequence, either adding or subtracting. Next one is a geometric sequence. Now on a geometric sequence, it's based on multiplication. And so you can kind of read this, and I'll go over this a little bit, but don't worry too much. This is actually way higher level math than you really get into. You'll see this kind of notation in calculus, I guess, but I'll go ahead and show it to you. So you have a sub n, which is your general term, where n is the nth term, like the first term or the second term or the third term. So like the first term would be a sub 1 times r, which is your common ratio. That's a thing you're multiplying each thing by each time. And then to the same general term, which is the n minus 1, which would be the numberth term minus 1, which would be the previous term, essentially. Or as your numbers go up, that's going to increase. So I'll show you what that looks like over here. So here's our geometric sequence: 1, 5, 25, 125, 625. You can probably see what the common ratio is. What are we multiplying each term by? 5, right? 1 times 5 is 5. 5 times 5 is 25. 25 times 5 is 125. And then it just keeps getting way big out of hand, right? So our first term is going to be 1. So that's going to be our first term is our a sub 1, which is going to be 1. And so when we plug this into the general form, this a sub 1, our first term is 1. The next one is a common ratio r, which we said was multiplying by 5. Okay, and then the n minus 1 is going to be whatever the term we're on minus 1. Okay, so when we're doing the a sub 1, we plug in 1 for the n. So 1 minus 1 is 0. Anything to the 0th power is just going to be 1. So that 5, that common ratio, goes away, and it leaves us with just our first term, which is 1. But what happens on our second term? So a sub 2. Now it's going to be 2 minus 1, which is 1. 5 to the first power is 5. 5 times 1 is 5. So that's where we go from 1 to 5. And then after that, it's going to be to the second power, which is 5 squared, which is 25. Then it'll be 5 to the cubed, which is 125. 5 to the fourth power, etc., etc. So anyway, that's how the general formula works. I'm not going to ask you to do anything like that in this course. I just wanted to go ahead and show it to you because I think it's kind of cool. And if you get into the higher level math, you're going to see it again. So another thing, which also you'll see again in calculus, like with converging or diverging series, infinite sums and series, is an alternating geometric sequence. So geometric tells us it's multiplication again. The alternating part tells us that it's going to be going back and forth between a positive and a negative value. Now this happens every time our common ratio is a negative value. So if our first term is 1, so we're saying our first term is 1, then the common ratio is negative 2. So let's just multiply by negative 2. So 1 times negative 2 is going to be negative 2. Okay, negative 2 times negative 2 again is going to be positive 4, then times negative 2 again, negative 8, and again, positive 16. So notice what's happening. We're alternating between a positive, negative, positive, negative, positive, negative. So it's just like the geometric sequence we had before, except now we're alternating between positive, negative, and the next one will be a negative value, right? Okay, so the reason that happens is because over here with our common ratio, it's negative. So when it's to the 0th power, it's going to be 0 and it goes away. We just have our first term. The next one is going to be to the negative 1, right? Anything to the 1 for the first power is going to be the anything. So negative 2 times 1 is negative 2. And then after that, we have squared. When we square negative, it becomes positive. So anytime we have a even exponent, it's going to make it positive. Anytime we have an odd exponent, it's going to be negative again. So you're going to see it play out where it alternates back and forth between positive and negative, because negative 2 squared is going to be a positive 4, and that gives us the positive 4 over there. And then again, then would be negative 8, then the next one would be 16, etc., etc. Okay, so anyway, again, I'm never going to ask you to do anything like this. I just want you to see how the general form works. If you get it, that's great. If you don't worry. You'll see it again when you get to calc. All right, so the other thing is that music itself is just repeated patterns over and over again. So if you like music, and what's kind of cool is a lot of my students, you guys are in music, are familiar with music, so you'll hopefully enjoy this. So there is 4 chords that we usually play in the key of C, which has no sharps and no flats, so we like the key of C. You can play the key of C in piano because it's just all the white keys. As long as you don't touch any of the black keys, it would be an accidental or whatever. You're in the key of C. Congratulations. So our 1 chord is a C major. Our minor 6 is A minor. Our major 5 is going to be a G, and our major 4 is going to be an F. So those are the chords. The progression of the chords, you usually go 1, 5, minor 6, 4. You don't always go that, but it is very common. In fact, it's such a common progression of chords. I'm going to show you this quick video about the axis of awesome, 4 chords. It's pretty cool. I've shown it every year. I think you're going to enjoy it. So if you're ready to have music stuck in your head, that's great. I'm going to play as much of that video as you want. You can skip through it if you want, but I promise those songs are going to be stuck in your head. So anyway, go ahead, come back, and enjoy.
Recognize this?
Yeah, that's Don't Stop Believing by Journey.
And the cast of Glee.
Yeah, there's a few more songs with the same chords. Check it out.
My life is brilliant, my love is pure. I saw an angel, of that I'm sure. People killing, people dying, children hurt and you hear them crying. Can you practice what you preach? Won't you turn the other cheek? Forever young, I wanna be forever young. I won't hesitate no more, no more. It cannot wait. I'm your lipstick stains on the front lobe of my left side brains. I knew I wouldn't forget you if I could. Then I would. I'd go wherever you will go. Can you feel the love tonight? Nobody wants to see us together, but it don't matter, no. 'Cause I got
country
you.
road, take me home to the place where I belong.
I'm your biggest fan, I'll follow you until you love me. Papa,
I can't
live with or without you. Pictures of you, pictures of me, hung upon your wall for the world to see.
And she will be loved. Yeah, she will be loved.
When I find myself in times of trouble, Mother Mary comes to me.
No woman, no cry.
Yeah, Mama, this surely is a dream.
I come from a land down under.
Red, white, and blue. Funny things you do. America, America, this is you.
They say that Taylor was a good girl, never one to be late, complain, express ideas in her
I
brain.
need some love like I've never needed love before. I'm gonna make love to your baby.
Take on me
When I come around.
Take me on
When I come
I'll
around.
be gone when I want to. Save
Gonna
tonight
take a lot to drag me
and fight the
away
break of
from
dawn.
you.
Come
There's nothing that 100 men or more
I'll
could
be
ever
gone.
do.
Here I am once again. I'm torn into pieces. Can't deny it, can't pretend. Just thought you were the one in my head. I see you all over me in my head. You fulfill my.
All right, welcome back. So as you see, those 4 chords, the exact same progression of chords are used over and over and over again, is the same basis for almost all those songs, at least when they're in the key of C, which is pretty stinking cool. And so if you can learn how to play those 4 chords, you could play technically all those songs. The only thing that's changing maybe be the rhythm or the strumming pattern or something like that, or maybe some effects that they're playing with the keyboard. And then you put it all together and you've got all these different songs. So what's silly is that those same 4 songs, they can make sound differently in some slight variation to come up with all those different songs. So even you can be a star musician. And the big secret about music is that it is really, really simple, especially when you're just playing chords. And beautiful music can be really simple music. It doesn't have to be complicated for it to be gorgeous music. So let me show you how to play on the guitar. And I could have made a video showing you me playing on my guitar, but it's late and I didn't have time. So instead, we're going to do what I do in class. So made this lovely guitar with all the struts, and the strings. And look, the strings even have varying thicknesses. Oh, it's so fun. Anyway, so on our guitar here, we can play in the key of G with bar chords pretty easily, or the key of C. So the first thing is with bar chords, you kind of saw how these chords are formed, by the way. You can see that if you can read that. But with bar chords, it's the same pattern, just raised up or lowered down. So for example, this is the E major chord, which is probably one of the easiest ones to play, and probably one of the first chords that you would learn how to play. So it's just the numbers are the number of your fingers from 1 all the way to 4 or whatever, with thumb being 0. And anyway, so that's how that is played. So that would be an E major chord. Then if we slide up to the first fret and bar the first fret, so it's called a bar chord with our first finger, that would be an F chord. And we go to the 3rd fret for G, the 5th fret for A, the 7th fret, oh that's funny over there, is B, B major, and then C, C major, and then D, and then E, and it repeats all over again. It's at the 12th fret. That's what's special about the 12th fret. And then the 13th fret is going to be exactly the same as the 1st fret, which would be an F chord, just like we had the F chord right down here. And you can keep going as high as you want, basically, as high as the guitar will let you. All right, so kind of cool. So if we wanted to play those four chords of songs, we would start out on the 1, which is going to be the C, and the C major, okay, and then we go to the G, which is the 3rd fret, and then the A minor, which is going to be the 5th fret, but we lift this finger up so that it's a minor chord, and only slight variation, and then back to the F, which is the 4. So we go from the 1 to the 5 to the minor 6, and then down to the 4, and then back to the 1 to the 5 to the minor 6, and back to the 4. Over and over and over again, just counts of 4. 1, 2, so essentially, it's kind of fun. I feel like I'm playing guitar, which is kind of fun. So like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And that's how they play every single song you just heard. Does that sound difficult? No, it's not difficult. It's so easy on guitar. You could probably sing while you play guitar, and you're not even thinking about it. What fun, what fun. Okay, more patterns in math. Here we have Pascal's triangle, which actually shows the binomial expansion, which is uber important in statistics and lots of other fields of mathematics. So across the one diagonal here, we have the ones. Then the next one, we have counting numbers. We're just adding the next one. And the way these are formed is we add the 2 columns above it. Or yeah, the 2 columns. So 1 and 2 is 3, 1 and 3 is 4, 3 and 3 is 6, 4 and 6 is 10, 10 and 10 is 20. You can see how it's done. And these are the binomial expansions. So when we take anything, this binomial, and we expand it to the 2nd power, then the coefficients are what are going to be shown here. So the 1, 2, 1, if we go down to the 2nd number here, is going to be 1, 2, 1. So this is a 0, 1, 2, so 1, 2, 1. And the next one, if we did this to the 3rd power, it would have exponents of 1, 3, 3, 1. And I could show that, but I don't want to confuse you or anything. But this 3rd row here, triangular numbers, shows up in some really cool places, including a really fun problem on our homework today. So triangular numbers, why are they called that? This pattern here, it's like factorial, but we're adding, if you guys know what factorial is, like for instance, 4 exclamation point is really 4 factorial, which is 4 times 3 times 2 times 1. Anyway, so it's like factorial, but we're adding. So the first one is 1, and then we add 2, and we add a 3rd row, then a 4th row, then a row 5, then a row 6, etc. So we're adding one more each time, or going all the way back down to 1. And these are where you can make your equilateral triangles, where your sides are 1 by 1, 3 by 3, 4 by 4. 6 by 6 and 7 by 7, and it just keeps going on forever and ever. Okay, so anyway, these are the triangular numbers, and you'll see those numbers 1, 3, 6, 10, 15, 21 right here. 1, 3, 6, 10, 15, 21. What? That's so sneaking cool. I know, pretty awesome. I believe there's a formula for triangle numbers, or I think I came up with one last year. I just don't remember it off the top of my head. All right, so another thing is recursively defined sequences. So we got arithmetic patterns. We got, what was the other one? Geometric patterns. Then we have the alternating geometric patterns, which are the ones that go back and forth, positive, negative. Now we have recursively defined sequences, which are more complex, but also pretty cool. So let's see if you can find out the pattern. We've got 2, 3, 6, 3, 6, 18, 6, 18 something. So can you see when I say it that way what's going on? So 2 times 3 is 6, 3 times 6 is 18, 6 times 18 is 108. so cool. 18 times 108 is an even bigger number. Hey, you're supposed to animate, but it didn't work. That's fine. All right, so this is called a recursively defined sequence. This is with multiplication. You can also do it with addition, and when we do it with addition, it's called the Fibonacci sequence, which is a very famous sequence. In fact, I even got a video, another short clip. I'm going to show you about the Fibonacci sequence. But first, we just add. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. Okay, 8 plus 13 is 21, 13 plus 21 is going to be 52. That's not right, is it? That's totally not right. Did I do those right? Okay, that is 13. That is 21. That is 34. I think the next one. Yeah. Then after that would be 55. Anyway, I know you guys will correct me because you guys are paying closer attention than I give you credit for. So thank you for that. So Fibonacci sequence is really cool about it. Leonardo da Pisa, he's actually the guy who came up with a bunch of problems. Like, man, I wish I knew what it was called. Anyway, he came up with a bunch of math problems, and he was a merchant, and he would travel back and forth between India and Europe through that little place in between, near the Gaza Strip. Anyway, so he would go back and forth from one place to the other, and when he went to India, as a mathematician, he would figure out what they were doing in mathematics, and that's where he noticed the Hindu-Arabic number system, like 1, 2, 3, 4, 9, all the stuff that we do, like place value and stuff, and the numbers 1, 2, 3. Those numbers that the whole world uses now, those actually came from India, which is kind of cool. And because it was such a good system, the place value system and the Hindu-Arabic numbers, instead of using what they were doing back in Europe, which was Roman numerals, which no one likes Roman numerals, and well, they like them, but they're not very good. They're really difficult to do math with and stuff like that. Anyway, so he brought that system to Europe, and through merchant trading, he's like, hey, look, there's a better system. And slowly the rest of the world adopted it, which is really cool. So the Fibonacci sequence was named after this guy. His name was really Leonardo of Pisa, and he also went by the name of Fibonacci. Anyway, kind of cool story behind him. There's a good story about how the Fibonacci sequence, like how a story that goes behind the numbers, but actually where you see it show up is in nature all over the place with the golden ratio and Fibonacci's spiral, which is really, really cool. And I'm going to show you a video about it. So we'll go ahead and watch the video, and then I'll explain a little bit more. So Fibonacci in nature, here you go. Boom.
Sequence begins with the numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, and continues indefinitely. Each number is obtained by adding the last two digits together. If we were to take a perfect or golden rectangle, break it down into smaller squares based on Fibonacci's sequence, and divide each with an arc, the patterns begin to take shape. We begin to see Fibonacci's spiral. The spiral in and of itself is insignificant. Its importance is revealed in where we find it. Take, for example, the sunflower. The display of its florets are in perfect spirals of 55, 34, and 21, the sequence of Fibonacci. The fruitlets of the pineapple create this same spiral based on the sequence. The pine cone does the same. As currents move through the ocean and the tide rolls onto the shore, the waves that bring in the tide curve into a spiral that can be mathematically diagrammed onto a plot at the points 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. Buds on trees, sand dollars, starfish, petals on flowers, and especially the nautilus shell are formed with this exact same blueprint. With each segment of growth, the nautilus adds to itself one more value on Fibonacci's scale. This blueprint can be seen around us on a small scale every day, but the greatest example of all is directly above our heads. At an average of 100,000 light years across, even the spiral of the galaxies above us are formed with the exact design that the tiny shell is formed. This sequence, or blueprint, appears to be the trademark of a designer.
All right, welcome back. I hope you enjoyed that. So really cool stuff. The idea even goes even further behind it, explained in other videos, which I will link if you are interested. But Vihart's got some videos. It's another YouTube channel I think you guys will really enjoy, and I'll link some of those videos or playlists or something that you want if you want to watch. Warning to talk really fast, but the idea behind the Fibonacci sequence is really cool. How essentially, if you had leaves that were being spiraled up going up the stalk, how the leaves would not overlap each other, so that they would have the most photosynthesis and the best, most efficient growth, essentially, with whatever pattern it did. So lots of different ways you can think about how this developed. So some people would say, like, over time evolution would benefit those that would have an adaptation that would allow them to grow more efficiently than the others. Others would say that no, this was like built into the DNA, this code that allowed the plants to be able to grow in a more efficient pattern. And there's actually only very few plants that actually diverge from that pattern. So some people would lean more towards thinking that evolution kind of explains it, and how some would outperform other species that didn't have this adaptation, and then others would lean towards no, this kind of points towards an intelligent design from an intelligent designer who had much more say in like how the DNA and how the building code would come up. And even human beings being, the smartest, things that walk the earth, even we didn't realize that this was going on, even though it was happening ever since the beginning of time, which kind of points to, wow, so there's something out there that's smarter than us. And and then people be like, whoa, God, or Illuminati, whatever. So I'll let you come to your conclusion what you think it is, but regardless of what you think, it's math. It's been there. We now kind of explain it and see it all over the place, and it's really, 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 really stinking cool from multiple different disciplines. So we can all agree on that, even if we disagree on where the world started and all that great stuff. So fun stuff. Moving on from Fibonacci sequence. So that's it. If you'll go ahead and get out your assignment, hopefully the lecture, I've got the other stuff that I put in there, obviously making it much more entertaining and fun. I hope you guys enjoyed that. Let's go ahead and get started with the assignment. The assignment should be pretty easy, but there are some challenging questions in there for you as well. So looking at number 1, we want to be able to state the next 2 terms in our sequence. So we're going from 5 to 11, and then 11 to 6 or 18. So the first thing I want to do is see, what is it, arithmetic or is it geometric, or what's the pattern? So if I'm going from 5 to 11, I'm adding 6, and then 11 to 18, I'm adding 7, and then from 18 to 26, I'm adding 8. So it's basically going to be, let me push that again. Okay, so plus 6, then plus 7, then plus 8. So what would come next? Plus 9, which would give us 35, and then plus 10, which would give us 45. Okay, so that's an arithmetic sequence. It is getting bigger. We're adding 1 more each time, but it's still considered an arithmetic sequence. Alrighty, so sequence A, we have a triangle, a square, a pentagon. So if we notice, each time we're getting 1 more side. So we go from having 3 sides to having 4 sides to having 5 sides to 6 sides, and then 7 sides would be the next 2, right? Which would be a heptagon, a hexagon and a heptagon or septagon. Those 7-sided polygons have 2 different names from the Greek and from the Latin. But anyway, so the other thing is I'm listing out the terms. So first term, second, third, fourth, fifth. And if we notice the pattern from the first to the third, we're just adding 2 to the number of term, and we add 2 more sides. So the second one, 2 plus 2 is 4, 3 plus 2 is 5, 4 plus 2 is 6, 5 plus 2 is 7, etc., etc. So it's just going to be 2 more than the one that we had before. So our formula for this, our generic term, is that the number of sides is equal to the nth term plus 2 more sides. Kind of cool. So how many sides would the 5th figure have? Well, 5 plus 2 would give us 7, right? So that would be 7 sides, and we would see that over here. So what about the 10th? Well, 10 plus 2 would be 12. What about the 14th? Well, 14 plus 2 would be 16, right? And we don't need to draw those out. We understand that it's just going to increase by 1 each time, and it's going to be 2 more than the nth term that we're dealing with. So anyway, kind of cool, and you see how these conjectures or these general forms are really helpful. Once you find that out, you kind of find the key, or the equation or whatever, you can plug it in to find out what the nth term is. So here's another one. This one's really fun. So sequence B, -5, 4, -2, -5, 4, -2, -5, 4, -2. You notice that we have a reoccurring string of 3 elements, right? So what's the length of the shortest string of elements? That's going to be 3, right? Because we repeat after every 3. It just starts over. So the key, I guess we'll go ahead and I'll show you the key in a little bit on this one. So what's the 10th figure? So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So what comes after the -2? Well, after -2 is a -5, right? Well, then we could do the 15th figure. We could start over. So that was the 10th. So the 11th would be here on 4. 12, 13, 14, 15. So it should be -2. All right. So yeah. And then it's going to be -2. Yeah, it is. But let me show you the other way to do this, which is actually kind of cool. So we can solve this using division. So let me pull up a calculator. Oh, it's way over here. So we're going to use something called a division algorithm, where we take the number of sides and then we're going to divide it, we take the number, or our nth term, we divide it by 3, and we look at the remainder. So for instance, when we have 1, this is the first term, 1 divided by 3 is 0 with a remainder of 1, right? 2 would be 0 with a remainder of 2, and 3 would go in evenly with a remainder of 0. And you're going to see the exact same pattern over and over again. So when we get to the fourth one, 4 divided by 3 is 1 with a remainder of 1, okay, and then 5 would be 1, 3 goes in 1 time with a remainder of 2, and 6 goes in evenly twice with a remainder of 0. And you'll see the same thing whenever we get to 7, 8, and 9 as well, and then 10, 11, and 12. So that's the reason why this works, which is kind of cool. So you take the number of shortest number of string, divide it by that, and then you can label your remainders above those first ones. So really cool stuff. So for instance, for the 10th figure, what we would do is we would do 10 divided by 3, which is going to be 3 times with a remainder of 1. You notice this 1/3 with a repeating 3. So if we have a remainder of 1, that means the value is going to be -5. What about 15? Okay, so 15 divided by 3 is going to go in evenly, obviously, 5 times, with a remainder of 0. And anytime we have a remainder of 0, that means that our value is going to be -2. What about the 74th? So instead of counting over the top of these 74 times, we got time for that. We got homework, right? So 74 divided by 3 is going to be 24 with a remainder of 2, so that's 2/3, right? So 24 with a remainder of 2. Remainder of 2 means the value is going to be 4, and sure enough, it will. What about 1087? Okay, so 1087 divided by 3, which is going to give us a remainder of 1, right? So remainder of 1, which would have to be -5. I got to fix that. Okay, cool. So anyway, if I asked you for any term, you could tell me what it was whenever we know. It's a little trick here, which is kind of nice. Hope you enjoyed that. And understand that that is pretty advanced stuff, but hey, it's cool. That's why you're in honors. Making your brain hurt, which is good because it means that it's growing. All right, number 20. So we have 17, 23, 29, 35. So are we adding? Let's see. Okay, so we would be adding 6 each time. Yeah, it looks like we're just adding 6 each time. So plus 6, and then we do plus 6, plus 6. So next would be 47. Then after that would be 53. Okay, so just an arithmetic sequence where we're adding 6. The next one looks like we're adding 2. Okay, so plus 2. Then we add 4. Okay, so what do we add next? 6. Okay, and then 8. So next would be plus 10, which will give us 42. Then we do plus 12, which will give us 54. My handwriting. It's okay. 23. Ooh, notice the positive, negative, positive, negative. So remember what this is. It's an alternating geometric sequence. So the question is, what are we multiplying by each time? So 2, 4, 8, 16. Looks like we're multiplying by a common ratio of -2, where our first term, the a sub 1, is going to be a 2. So the next one would be a -64, and then after that would be a positive 128, right? Okay, and then number 25 says, what are 2 different ways? So a pattern has not been established yet, so there's more than one way to answer these at this point. What are 2 different ways we can continue this pattern? So we have 1, 1, 2. So what if we were adding 0, then we added 1, then we add 2, right? Then we would add 3. So that could be one way we could do it. So 2 plus 2 would be 4, and then if we did 4 plus 3, that would be 5 or 7. Oh gosh, it's late. You guys know what I'm doing. That's why I type these out, just in case I make a mistake. And then the other one, 1, 1, 2. Okay, what if we did a recursively defined sequence, such as the one we just learned about? That was really cool, named after that one guy, Leonardo da Pizza, known as Fibonacci, which would be a recursively defined sequence with arithmetic. So it's addition. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and then 8, and then 13, etc., etc. Okay. All right, number 28. This one causes all kinds of problems every year. So first we start out with an angle of 90, and then we get to 135. And then we get to 157.5. And then we get to another one, which we don't know yet. So what are we doing? Well, what we're doing is we're adding half the leftover distance to a straight angle. So what's half of 90? That would be 45 degrees. We're going to add 45 to that, which gives us the 135. So we just added half of the last one. Then we're going to add half of what's left over now. So half of 45, which is 22.5, and add that to the 135, which gives us the 157.2. And then half of the 22.5 would be 11.25. Add that to the last one, which would give us 168.75. Yeah, 168.75. Whew, that was difficult, but we did it, and we did it together. All right, next one, and this is the last one, I think. Yes, last one, and this is a famous and fun problem. So how many handshakes occur? 7 people meet, and they all shake hands with one another. How many handshakes occur? So this is a fun riddle. What I would recommend is you pause it, try to think through it. You can use this, these are the 7 people, so this is 1, 2, 3, 4, 5, 6, 7. You can use that if it helps to try to think through in your mind how we might work this problem. And then you can unpause the video and I'll show you the solution. Okay, so one of the solutions you probably did was 7 times 7, right? Because if you have 7 people and then you shake hands 7 times, the next person shakes hands 7 times, the next person 7 times, so that might give you 49. But if you think about it, the first person, how many hands does he actually shake? Does he shake his own hand? No. So the first person really actually only shakes 6 hands. So does that mean everyone's shaking 6 people's hands? Okay, so then 6 times 6, which would be 36. Oh, so 36 hands are being shaken. No, that's not it either, because if you think about it, if the first person goes around, he shakes all 6 of the other people's hands, then all those people no longer have to shake his hand, because one handshake counts for 2 people. So what about the second guy? He's already shaken hands with the first guy, but he hasn't shaken hands with the others. So how many hands would he have to shake? 5 hands. You can probably see where this goes from here, right? So the next person is shaking hands with these 2 who shook hands with him. Doesn't matter who initiates the handshake at this point. A handshake is a handshake. So he has 4 hands left to shake. And the next person 3. And then this person only has these 2 people left. And the last person has 1. By the time this person shakes the last person's hand, this person doesn't need to shake anyone else's hand because they just stood there with their hand out and everyone else walked by and shook its hand or whatever. So we want to add all these values together, which is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Wait, that sounds familiar, right? 1 plus 2 plus 3 plus 4 plus 5 plus 6. We're adding one additional one each time. Okay, kind of like factorial, but it's not. These are called triangular numbers. What's our triangular number for the 6th one? It is actually going to be, I believe, 21. So triangle number T sub 6 is 21. So the first person had 6 hands to shake, and then 5, 4, 3, 2, 1. So the total number of hands that were shaken was 21. As I said, triangular numbers and patterns would come back, which is so freaking cool. You're welcome. Patterns are everywhere. They're in nature. They're in Pascal's triangle, even multiple layers of them all in Pascal's triangle. And it is so stinking cool. And if you knew statistics, I would tell you even more about Pascal's triangle and about other things as cool too. And when you get to calculus, you're going to notice all this stuff is like, whoa, it's so cool. I've already seen this before. You're welcome. I know this was a long video. Hopefully it's a short and an easy assignment for you to do, and I hope you enjoyed it. I apologize. I will try to make the video shorter. This is, man, it's just such a fun day. Hope you guys have a good one. Bye.